It is now my pleasure to welcome not just the next speaker, but also our host here from MIT, Professor Farnaz Nirouri from the ECS department. Among her many awards, she is the DARPA Young Faculty Award winner, NSF Career Award winner, MIT Outstanding Educator, and also a Miller Postdoc Fellow at UC Berkeley. Go Bears. Welcome stage today. Her research in extreme NEMS, nano-electromechanical scale systems, it pushes the limits for miniaturizing sensors to a whole new level. Looking forward to your talk very much.
Thank you. Thanks. Excellent. Hello, everyone. It's wonderful to be able to host you here on MIT campus. The weather is nice, so we're very pleased that you can all be here today. Thank you also for giving me a chance to be able to share with you some of what my group here at MIT focuses on. I don't have to do much convincing of this audience that microelectromechanical systems over the past decades have had tremendous impact in diverse disciplines and application areas. Miniaturization of MEMS also to the nanoscale has led to quite a lot of new and emerging opportunities in diverse areas: sensing, actuation, information processing, reconfigurable optics, photonics, metasurfaces display, just to name a few examples. Many of these devices, however, still are focused on dimensions that are hundreds of nanometers in size, leaving behind dimensions that are smaller, less explored. And you can imagine it's enlarged because of the fundamental limitations and challenges we're facing in order to be able to access these dimensions, but also be able to make electromechanical systems at these dimensions reliably. Now, these dimensions are interesting because there is quite a lot of new physical phenomena, at the same time, unique material properties that only happen at these dimensions. So if we could access these dimensions and create reliable devices at this scale, then we can open up many new opportunities for improved device performance. So that could be improved sensitivity, speed of operation, energy efficiency, but importantly, also be able to develop fundamentally new opportunities for devices with new operating mechanisms, at the same time, functionalities. So that's part of what my group focuses on. And in order for us to be able to realize these prospects, it becomes very important for us to be able to come up with ways of designing new ways of being able to design and fabricate at this scale. And throughout the next few minutes, I'm going to try to give you an idea of that by just choosing a couple of examples based on our work. And in particular, I'm going to pick an example based on designing energy efficient electromechanical switches. So as you're probably aware, electromechanical switches in the most simplest form would look like a relay that I'm showing you here on the screen, where you have movable electrodes, you apply a voltage electrostatically, actuate your device. As the contacts come into contact, your device turns on. If your elastic restoring force is sufficiently large to overcome surface adhesive forces, you turn off your device. And this mechanical process allows electromechanical switches to have an abrupt switching performance with near zero off-state leakage and a very large on-to-off current ratio. So that allows them to become a suitable platform for energy efficient applications, complementing conventional transistors. But of course, what I'm drawing here for you is just a schematic, an ideal case. And before we can actually reach this ideal situation, there are quite a lot of challenges that have to be overcome. And I'll focus on those by zooming into the switching gap. So in an electromechanical device, there's a movable electrode, surfaces that are nanometer distances away from each other. They experience large surface adhesive forces. And these forces scale with the switching gap dimension. So take your switching gap, going from a gap of 100 nanometer in size to 1 nanometer. Just in van der Waals forces alone, you're going to get at least 6 orders of magnitude increase in surface adhesive forces. And that causes the surfaces to experience large surface adhesion, leading to stiction in these devices. Now, that makes it difficult to be able to miniaturize switching gaps. And that's a critical step to be able to move towards energy efficient application by lowering the switching voltage in these devices. At the same time, this surface adhesion causes the device to experience a hysteresis in operation. And that also sets a limit on how energy efficient you can make your devices. And in extreme cases, the adhesion can be permanent. So you're going to get a premature device failure, which is not ideal. So for us to be able to move towards a low voltage, low stiction device, it becomes very important to be able to control surface forces at the extreme nanoscale dimensions. And I'll tell you how we go about doing that using molecules as nanoscale building blocks in electromechanical devices. So molecules are made through chemical synthesis from bottom up. So we have atomic precision in defining their structure and composition. Just so that we're all on the same page, here I'm showing you a molecule with 8 carbon atoms. It's just 1 nanometer in size. So the structure, chemical composition, mechanical properties of molecules collectively is what we use to try to achieve this nanoscale force control to allow us to be able to achieve miniaturization of electromechanical devices. So as I said, we have atomic precision in designing these molecules. One advantage is we can make these molecules with functional groups that we desire and allows them to be able to spontaneously assemble onto a desired surface, for example, the contacts of your device. So here I'm showing you a molecule of polyethylene glycol thiol, where the sulfur, hydrogen, or thiol group allows the molecule to selectively assemble onto surfaces like gold. So this is a transmission electron microscope TEM image of a gold surface without any molecular layer. Here I'm showing you the surface functionalized with 3 nanometer thin PEG-thiol molecule. Now, through the choice of the molecule, you can very precisely tune the thickness as you wish. Another advantage of molecules is that you can change the composition so that you can tune the surface interactions. To give you an idea, here I have a fluorosilane molecule. The silane end group allows functionalization onto surfaces like silicon oxide. The fluorocarbon end allows us to make the surface assume a lower surface energy property. So here is water contact angle on a surface of silicon. And if the surface is functionalized with a monolayer less than 1 nanometer thin of this molecule, we're going to get drastic change in contact angle, suggesting how you can engineer the surface interactions through use of just a monolayer of molecules. So by being able to integrate these molecules within electromechanical devices, we can lower the surface energy and as a result, lower the adhesion experience between the contacts. So here I'm showing you a scanning electron microscope SEM of a MEMS relay. This is micron in size. So the cross section here shows you how you have a top membrane separated from the bottom source, drain, and gate. An applied voltage causes the membrane to collapse, turning on your device. And as the voltage is removed, you're going to get recovery. And of course, as expected, because of surface adhesion, this is associated with a hysteresis in operation, which sets a limit on how energy efficient you can make this device. So now if we functionalize the contacts in this device with this molecule, fluorocarbon and alcohol end group, allowing its assembly onto the tungsten contacts of this device, we're able to operate the device at extremely reduced hysteresis voltage, less than 30 millivolts in this case, providing an opportunity to be able to have these devices operate at lower energy. So this work is done in collaboration with Professor Sujay King-Liu and Juncha Wu at UC Berkeley. So the molecules can also serve as a structural component for designing electromechanical devices. So in addition to just functionalizing the surface to play around with surface interactions, it's also possible to leverage the structure to miniaturize your device fully. And we do that by leveraging both the structure of the molecules and mechanics. And I'll give you a couple of examples of each. So imagine instead of a switching gap that's made out of air or vacuum, we now have molecular springs in the gap. So the molecules, depending on their mechanics, can provide an elastic restoring force to balance up the surface adhesive forces. That first helps us be able to fabricate structures that are much smaller than what conventional fabrication techniques would allow to fabricate reproducibly and reliably. So in this particular example, sub 10 nanometer gaps. At the same time, now if you actuate your device, the elastic force in the molecules can actually help you be able to modulate the surface interactions such that you can have this small device operate in a controlled and reproducible manner. So if you make these junctions small enough, and with that I mean less than 3 nanometer in size, then you're going to get conduction through tunneling, quantum tunneling through these junctions. So you no longer need direct contact between your metal electrodes, but you can get conduction through tunneling. Now, tunneling current changes exponentially as a function of reduction in the tunneling gap. So you can imagine by tuning the gap, now you have a new mechanism for designing electromechanical switches. Of course, fabricating a molecular gap that's sub 3 nanometer in size is not the most trivial task. Top-down fabrication techniques are often insufficient. But the advantage of top-down techniques is that they're versatile. They can allow us to achieve complex structures that are also active. On the other hand, bottom-up processes have been developed with the promise of being able to assemble into geometries with nanometer precision. Largely bottom-up fabricated structures are passive and they're very simple in form. So what we do in our group, we come up with ways of integrating these two techniques so that at scale we can fabricate these structures, but with that can be externally probed and active, but with nanometer down to sub-nanometer precision. So here's an example of one of these devices fabricated in form of a lateral relay. So the SEM image here shows you electrode 1 and 2. Electrode 2 is movable. Electrode 1 is stationary. So you go through a normal top-down fabrication, fabricate such a relay. We deposit our molecules, and through this process, intentionally induce collapse of our relays such that the molecule is sandwiched between the gap. So an original gap fabricated at much larger dimensions can now be reduced to sub 5 nanometer in size. Now, if you fabricate such a device using this fluorothiol molecule, you can get a current voltage characteristics exponential in form expected of quantum tunneling. So if you compare this to what you theoretically would expect, you can see that there is a larger discrepancy between your theory and experiment at larger voltage values. Now, if we change our model so that it takes into account that there's a molecule in the gap which can compress throughout this process, you get the green line, which shows you a much better fit to your experiment. Now, in getting this best fit, we estimate the Young's modulus of the molecular layer to be on the order of 0.2 gigapascal, which actually matches what you would expect for this molecule if you were to measure it through other experimental means. So in this process, the molecule undergoes about 3 angstrom compression in order to give you the times 10 modulation of the current. And to put that into perspective, that's on the order of 2 carbon-carbon bonds. So molecules could give you controlled modulation of very small dimensions. Now, if you test this device repeatedly, you get reversible performance. You can see here on the current voltage characteristics. So if you compare that to the case where the device did not have the molecules, you can see how even though the first run of the device could be successful, the devices then undergo shorting. So the presence of the molecules are also important in order to be able to make the process reversible. So what I showed you here, though, only gave a 10 times change modulation of the tunneling current, which wouldn't be sufficient for a good switch. So what we would want to do is modify the design so that we can actually get a much larger modulation, a few orders of magnitude. And that can be done by changing the mechanics of the material that's within your switching gap, allowing us to use this as a platform for low voltage induction-free electromechanical switches, what we call squeezable switches or switches. So this is a particular design that we developed and fabricated. So in this particular example, the gate electrodes are used to electrostatically actuate the switching gap, modulating the tunneling current. And of course, as the voltage is removed, then the process can be reversible. So in this particular example, it is quite important to have the surface topography that you're seeing here in order to be able to keep your actuation voltage at its minimum, but at the same time minimize the off-state leakage. So we go ahead and come up with ways of being able to fabricate such structures. So in this particular example, I won't go through detail, but we've come up with a way of being able to fabricate the surface topography with sub-10 nanometer surface variation between the source drain and the gate electrodes. So in this case, here I'm showing you an AFM atomic force microscope topography image of an example electrodes. You can see that the middle two gate electrodes are recessed about 9 nanometer relative to the source and the drain. So an additional advantage of this technique is that it actually allows us to also achieve planarization of the surfaces. So here I'm showing you an AFM of a deposited gold film, give you on the order of few nanometer roughness. So, through the planarization technique that we have, the same film can be made sub-nanometer smooth, which you can imagine can be very critical when you're trying to make devices that are on the order of the roughness that you have. So you go ahead, fabricate the bottom electrodes. The molecules are assembled through a self-assembly process. And the next step would be to introduce the top contact without inducing any damage to the molecular layer. Various different techniques can be used, and throughout years, we've developed a variety of techniques. One that I'm showing you here is using colloidally synthesized gold nanoparticles as actual building blocks for the top contact of these devices. So the SEM image shows these nanorods that are formed in solution. So when you take a droplet of them, put them on a surface, image them, they're disordered. So there needs to be a way for us to be able to pick and place individual of these rods exactly where we need them to be on our devices. So for that, we've developed this dielectrophoretic trapping technique. So we use the electrodes of our devices to actually induce an electric field, which through a process that limits the trapping to an individual particle can place the nanorods exactly where we want them to be. Again, an example of how bottom-up and top-down fabrication techniques allow us to achieve devices with unprecedented resolution. So now if I take the device and cut through it and look at it under high resolution electron microscope, you can see the gold nanorod top electrode, you can see the bottom electrode, and you can see the planarization that our technique achieves. So this is as deposited metal surface. You can see how rough it is, and the planarization itself actually allows us to achieve sub-nanometer smoothness. So if I zoom in, you can see how the molecular gap is well defined. And if we go ahead and test it, we do actually get the modulation of the current that we do expect for these devices. So initially, during the initial step, you see an exponential increase in the current as the switching gap starts shrinking as you apply a voltage. That is followed by an abrupt increase in current, and that's associated with the typical pull-in process, where your attractive forces are overwhelming the restoring forces. So your top contact accelerates towards the bottom. And this final section is just a limit set by the measurement tool that we're using. So here we're getting more than 3 orders of magnitude modulation of the current. And depending on the structure and the mechanics of the molecule, you can also get very low hysteresis here, less than 50 millivolt. So with sub 3 volt actuation voltage, orders of magnitude modulation of the current, as well as potential for sub 50 millivolt hysteresis, this becomes a promising platform in order to be able to design energy efficient, low stiction electromechanical switches, where you're leveraging quantum tunneling as the main switching mechanism. The devices also have fast operations. Our preliminary experiments suggest a turn on in the range of tens of nanoseconds. And depending on the type of the molecule you use, as you can see here on the slide, you can tune the nonlinear current voltage characteristics you get for these devices. So you can tune that depending on the applications you have in mind. So applications, of course, not limited just to an electromechanical switch. So just to give you a brief overview here, we've used it to create these optoelectromechanical resonators in the form of nanoparticle on mirror plasmonic structures, where the optical response of the structure is heavily dependent on the structure and geometry of the gap that you have in your plasmonic resonator. So you can see that we can get as much as 50 nanometers spectral change in spectral response of these optical structures as a function of just nanometer change in the switching gap. A step towards this is to be able to fabricate these structures at scale. And we do that again by implementing a technique based on integration of top-down and bottom-up techniques. So we start with, again, scalable synthesis of colloidal nanoparticles, here nanocubes as our building blocks, and we come up with ways of being able to spatially assemble them in the order we desire. So you can see here on the dark field image, assembled nanorods. So every green dot you see is an individual nanocube. And the nanocubes can then be transferred onto arbitrary surfaces, in this particular case, a metallic mirror, so that you can create your plasmonic resonators. The resonators show very reliable and consistent response, and that's a huge improvement compared to what you would get through conventional fabrication techniques for these type of resonators. So if I take one of these structures, cut it through again, you can see the metal molecule metal geometry. And if we go through thermal actuation of these devices, just to probe the extent of modulation that we can get, you can see that by just changing the temperature by 25 degrees, we can change the spectral response by about 2.5 nanometer. And this can be done reversibly. This is very detectable optically, and that corresponds to only about 30 picometer modulation of the gap. So you can imagine this can be a good platform for highly sensitive sensors, as well as with a very low operation energy. So with that, to summarize, I hope I was able to give you an idea that there is many opportunities at the extreme nanoscale for electromechanical system. Of course, nanofabrication and ways new mechanisms of operations become a core problem to solve for these opportunities to be leveraged. I introduced to you use of molecules as anti-stiction coatings in electromechanical system, extending that to create these tunable tunneling junctions and using them as a platform for low energy switches and extending that for tunable plasmonic structures and metasurfaces for various sensing applications. With that, I would like to thank my group, of course, collaborators at Berkeley and MIT, NSF and DARPA for funding the project, and thank you all for listening.
Thank you, Professor Nirouri. And I understand you serve on the DEI committee at MIT, is that correct?
I do, yes. Maybe I can share a little bit. So I do serve on our DEI committee in the ECS department, my home department. We do actually take very seriously DEI efforts here at MIT as well. Our department over the past few years, we've developed quite a lot of programs, two of which Thriving Stars and Rising Stars is developed to increase gender representation amongst our PhD students. The main point is to be able to develop a community for our students throughout their PhD program, and when they start applying for their future jobs, to be able to have mentorship and guidance and also support generally. So those have been quite successful. One that I personally have benefited from when I was a PhD student is the Rising Stars. It's a workshop that brings students together and teaches them how to apply for faculty positions, and also provides a visibility for them. So hopefully we can have similar programs, but for those students who would like to join industry, and perhaps we can have your support for that.
Thank you very much. Do we have any questions, Professor? We have Lauren.
Thank you. I really enjoyed your talk.
Thank you.
It was an interesting combination of a bunch of stuff I've also done in different ways and places over the last 10, 12 years. So it was very fun. My question for you is related to fabrication, because that's kind of where I fall now in fabrication techniques and approaches and stuff. What do you see as being the key things that the industry would need to work on to scale things like what you're working on into actual commercial devices?
So a lot of what I showed you, actually, thanks for asking that question. So they do involve new fabrication techniques. So if you come to my lab, we have our home built setups that are small. We can manage maybe up to a few centimeter by centimeter substrate. There is not necessarily a fundamental limit in being able to scale. It's just that we don't have resources to be able to scale the same techniques to larger scale, whether it's wafer scale or roll to roll processes. That's the main goal. So just having industry partnership to begin with would be very helpful for that. And another thing would be yield. So the larger the area gets, say, for example, our nanoparticle assembly techniques, it's on the order of 99% yield at the centimeter by centimeter scales that we're working with. Now imagine trying to scale that to 4 inches, 8 inches. The yield can be reduced. So being able to also address that would be one of the key problems to solve.
I think we have time for one last question.
Yeah, hi, this is Xu coming from Nanomicro. So we're doing a one switch building product. So I like your talks a lot. So question here, when you're putting the anti-stiction coating on a contact surface, how that going to affect your contact resistance? That's my first question. And the second question, what's the durability of the coating film? Have you basically passing like a binding contact for like a couple billion cycles?
Yeah.
The anti-stiction film still there?
Yeah, that's a great question. So, so the performance of the molecules vary drastically with the type of molecule. The shorter molecules, so the anti-stiction coating ones, are actually quite stable up to temperatures around 400 degrees Celsius. So those actually can go through quite a lot of cycles. Now, depending on the structure of the molecule, they can affect your contact resistance. And I'm happy to show you some data afterwards where we have longer chain molecules where they can increase your contact resistance. So we change the structure so that instead of them being a linear chain, they can actually be having the same number of fluorocarbons, but be lateral, so branch to the side, to be able to reduce the effective contact resistance. So there are ways of being able to play with it, but if depending on the structure, that could be a challenge. For the molecules that are compressible, those are softer molecules, so they're not as stable with temperature and also cycling. That's actually an area we're working on at the moment to try to come up with ways of being able to improve that. But for those devices, the most we've done, the compressible ones, the most we've done are thousands of cycles.
Let's thank the speaker.
Thank you.